Okay, in this video I'm going to continue on my tutorials on thermodynamics and statistical mechanics. This is video number 40 and I'm going to discuss the free energy and its relation to equilibrium. I'd like to draw your attention to my website universityphysicstutorials.com. So the previous videos to this, there are four, we'll say, relevant ones. I'd like to point out, by the way, in video number 39 I listed the numbers on the previous videos incorrectly. Anyway, so this one, look at number 39 where I discussed thermodynamic identities in terms of the Gibbs and Helmholtz free energies and the chemical potential. Number 38 I discussed the chemical potential. 37 I discussed the Gibbs and Helmholtz free energies. And number 36 I discussed the most basic thermodynamic identity. So what are we trying to do here? We're trying to basically work out what do we need to do with the Gibbs and Helmholtz free energies in order to minimize or maximize the universe's entropy. Why? The universe wants, or it needs, I suppose, equilibrium. That's what drives most, or if not all, of the situations in the universe is equilibrium. So we want equilibrium. Now, in terms of the Helmholtz free energy F and the Gibbs free energy G and the entropy S, how do we get the universe in equilibrium? That's what we're trying to find out. Now, we already have kind of an answer to this because we know what the second law says. The second law says that for an isolated system, we know that the entropy tends to increase. The entropy tends to increase. Now, there's something which I glossed over when I was talking about the second law, and it's the conditions under which, or by which, the second law applies. And the conditions are constant volume and constant energy. The whole point here is, if you're in an isolated system with constant volume and energy, the entropy will tend to increase. Now, the reason the word isolated is important is because sometimes you'll hear and you go, hold on a sec, that's nuts, that's mad, I've been told that this isn't correct. But sometimes you might hear that entropy decreases. You might say, that's impossible. No, that's not impossible at all. What's impossible is that the entropy of what's improbable is that the entropy of an isolated system decreases. However, the entropy of the universe in general will always increase, but individual small parts of it, the entropy may decrease. So if you have an isolated system, the entropy will always tend to increase. But if it's not isolated, some parts of the system will try and decrease the energy, and some will try and increase, in order to maximize the universe's total entropy. Okay, so it's all about maximizing the universe's total entropy. So if you have one or more systems attached together, some of the individual systems may decrease their energy in order to maximize the universe's energy. And that's an important point. It's also important to note, by the way, the volume and energy are constant. Next, let's talk about a reservoir. Let's talk about a connected system. So, what do we mean by a connected system? Let's say I put my system, like let's say a particle, into a reservoir. So here's my particle, and I put it in a reservoir, and I call the whole thing together my universe. Okay? So think about, let's say, putting a single particle into space. That's like putting a particle into a reservoir. But what do we mean by a reservoir? What we mean, or we define by a reservoir in this case, is something which is, it's large such that it can give up or take in any amount or an unlimited energy and remain at constant temperature. So if you think about it, if you add a particle to space, say if the particle was, a hell of a lot hotter than space, well then the particle will give up its energy to space. However, in general, it won't heat up the universe. The universe will stay at the same temperature, or excuse me, the space will stay at the same temperature. So we consider space to be a reservoir. So if you think of a system where it's large enough that if you give up or take energy from that system, it will remain at the same temperature, then we talk about that system being a reservoir. Okay, and what I'm going to do is put a smaller system which doesn't satisfy those conditions inside a reservoir, and we call that together a connected system, or we're going to call it the universe. So in a connected system, once again, the total entropy of the connected system, ds sub t, or the change of it, of course, is going to be equal to the change in the entropy of our system plus the change in the entropy of our reservoir. And for constant volume and energy, this connected system is going to want to increase its entropy. So for a connected system, you want to increase its entropy. Alright, but that's where you have this particular definition of the increase or the change in entropy. Next, let's look at the thermodynamic identity inclusive of the chemical potential. We saw this in, I think it was video number 39. Yeah, I think it's video number 39. So we saw that du, the infinitesimal change in anything's internal energy, is Tds minus Pdv plus mu dn. Okay, so of course we can rearrange this as du over t plus Pdv over t minus mu dn over t is equal to ds. And that's the formula we're going to use. This is the formula for an infinitesimal change in the entropy of anything. So, as we spoke about in the past, there is a difference between a constant pressure, constant temperature, and constant volume, and so on. So what I'm going to assume is we're looking at a system where the temperature is constant, the volume is constant, and the number of particles is constant. Let's just look at a system like that and see if we can create a system like that, what would be the condition which will bring the universe into equilibrium. Okay, how do we satisfy the condition of bringing the universe into equilibrium in terms of things we already know? So if we look here, the entropy at the moment is a function, the entropy is a function of lots of things at the moment. It's a function of the internal energy, the temperature, the pressure, the volume, the chemical potential, the number of particles. Okay? However, if we say that the temperature is constant, okay, if we say the temperature is constant, grant. If the volume is constant, we get rid of this term, and if the number of particles is constant, we get rid of this term. So this function will come down to a function of the internal energy, the temperature, but not really, and that's really it, I suppose. So we can say it's kind of the temperature, but the temperature is constant. So what we're saying is ds is equal to du over t. So in these conditions, this is the condition for the change in the entropy. Now, I said a moment ago that the change in the total energy, total entropy, is the change in your system's entropy plus the change in your reservoir's, entropy. Now, we know that anything you change in the reservoir, we'll say the energy, is minus the change in your system because they're connected. Okay? So we can rewrite this as follows. We can say that it's equal, that the total universe's entropy is the system's entropy plus the reservoir's energy divided by T, or it's going to be equal to du over T of the system like that, minus d over T of the system like that, using this particular equation. Okay? So we can say that the change in the total universe's entropy is going to be minus 1 over T. This is a bit of a sleight of hand. We're going to have du minus T ds. Now you may or may not recognize this as the change in the Helmholtz free energy. So the point is this is the conclusion, that ds, the total change in the universe's entropy, is minus df over T, where df of the system, by the way, df of the system. So in order to maximize the universe's entropy, you need to minimize the system's F, and that's at constant temperature, volume, and number of particles. Okay, so that's that. Maximize the universe's entropy, minimize the system's Helmholtz free energy at constant volume, number of particles, and temperature. So I'm sure you can see what's going to happen when we're talking about the Gibbs free energy, so let's go ahead and do that. So let's think of a system where this time we have the temperature, of course, the pressure, and the number of particles fixed. What happens then? Well, this time our entropy function ds just becomes du over t, but this time this time we also have a p dv over t term like that. So it's going to be the exact same argument, and let's just fire away, excuse me. So that means the total entropy of the universe is equal to the change in entropy of the universe is the change in entropy of the system plus the change in entropy of your reservoir. So it's this, and we're going to have plus du reservoir over t plus p dv reservoir over t. Okay, we know that a positive change in the reservoir is anything, is a negative change in the system is anything. So we get the total entropy change is ds of the system minus du of the system over t minus p dv of the system over t. Okay, once again we're going to do a sleight of hand. Because what we're going to do is multiply above and below here by t. Alright, now if you multiply above and below here by t and factorize just like we did in the last time, we're going to get the following. We're going to have ds, or we'll say tds minus du minus p dv. Now if you're, I suppose there's a bit of an angle there, minus p dv. Okay, and I'm sure you've seen where this is going. It's going to be minus dg of the system divided by t. I need to put in the subscript here. So that means ds of the change in entropy of the universe is minus the change in the Gibbs free energy of our system divided by t. So this is a constant temperature, pressure, and number of particles. So to maximize the entropy or get equilibrium, we need to minimize the system's Gibbs free energy. Note the difference this time in temperature, pressure, and number of particles, where the last time it was temperature, volume, and number of particles. So for fixed temperature, pressure, and number of particles, the Gibbs free energy tends to decrease. So let's put it all together. Let's put it all together. And this is very important, and this is, I suppose, this really is the bottom line. So that so it's constant, okay, and tends to, sorry, now 1 second, your system tends to, okay. Like that. Okay, so we've three scenarios. At constant energy and volume, the entropy tends to increase. At constant temperature and volume, the Helmholtz free energy tends to decrease. At constant pressure and volume, pressure and temperature, I should have a number of particles there as well, the Gibbs free energy tends to decrease. Okay, that's really the bottom line. Now why is this important? Why is it, well, as you might say, why is this important? The reason is, and this is a big jump now. We know at the moment that the entropy is equal to k times the natural logarithm of the multiplicity. When we start doing quantum statistics, we'll find that the partition function z is very important. I won't really discuss what it means yet. But the point here is that later on we find that the partition function can be related to, is kind of analogous to the multiplicity. And the only reason we can make this analogy is because we find that the Helmholtz free energy tends to decrease in order to get into equilibrium. Okay, so if you're going to do quantum statistics at some stage later and you're going to talk about the partition function, you'll need the results of this video in order to do it. Okay, so thanks for watching. Please pass it to your friends, subscribe to my channel, and please visit universityphysicstutorials.com.